Bismillahirrahmanirrahim. So in previous lectures, we have talked about functions and then their types like one onto, and then we have talked about some other theorems and properties, so like invertible functions and composition of functions, and provided some theorems and then their proofs. Now we will give some examples to understand the topics more clearly. So the example one is determine which of the following mappings are 1 and onto. If R into R are 1 are onto R. Number one is of x is x plus 4. Number two is of x is x squared for all x in R. Solution. To show that function is onto, 1. We just have to show f of x is f of y. So to do that, let's solve number one. So let x comma y are in R. Suppose f of x is f of y, then x plus 4 is y plus 4, or x is y. Hence, f is 1. Now, f is onto R if and only if for all y in R there exists x in R such that f of x is y and let y in R if f of x is y, then x plus 4 is y, or x is y minus 4. So also y minus 4 is in R. Thus, we can take x to be y minus 4. Now, f of y minus 4 is y minus 4 plus 4 is y. Hence, f of x is y. So, hence, f is onto R. So number one is from 1 and onto. Let's try number two. Number 2, we note that f of x is non-negative real number for all x in R. This means that negative real numbers have no pre-image. So in particular, for all x in R, f of x is fx square, which will never be -1. And hence f is not onto R. Also, f of -1 is 1, which is f of 1. And -1 is not 1. Thus, f is not 1, 1. Thus, f is neither 1, 1 and onto R. Perfect. Now, let's talk about exercise 2. Says that number 1, late, we have a mapping Z into Z defined by following thing, that is f of x is given by x and 2x, x if x is even, 2x plus 1 if x is odd. Okay, and this is true for all x and z. Find the left inverse of f if one exists. The question is, find the left inverse of f if one exists. Number 2, we have a mapping f from z into z, which is given or defined by f of x is mod of x plus x for all x in z. Find the right inverse of f if one exists. Find the right inverse of f if one exists. Okay, solve this. you can use theorem. So solve one by theorem 1.5.18. So let's go back to that theorem. 1.5.18 says if we have two sets and then a mapping from A to B, when following assertions hold. Which one? One is f is 1 if and only if f is left invertible. So we just have to, these are vice versa. So if we want to show the left invertible, we want to show that f is 1. We want to show if we want to show f has a right invertibility, then we just need to show f is onto. So here we need to do that. Probably. So by theorem 1.5.18, f has a left inverse if and only if f is 1. Before we attempt to find the left inverse of f, let us first check whether f is 1 or not. So let x comma y in R and f of x comma y is f of y. Sorry, f of y is f of y. F of x is f of y. Then by definition of f, by definition of f of x is even if x is even and f of x is odd if x is odd. Thus, since f of x is f of y, we have both x and y either even or odd. If x and y both are even, then f of x is x and f of y is y, and so x is y. Suppose x and y are odd, then f of x is 2x plus 1 and f of y is 2y plus 1 and 2x plus 1 is 2y plus 1, or x is y, hence f is 1. Hence f is 1 and has a left inverse. Thus, there exists a function, exists a function g from z to z such that g of f is iz. Okay, I just spotted a thing. Here I need to take everything from z. Yeah. Okay, g of f is iz. Now let x is from z. Suppose x is even. Now x is iz of x, which is g of f x, which is g f of x, which is g of x. This means g of x is x when x is even. Now x is odd. Then x is iz of x, which is g of f of x, which is g of f of x, which is g of 2x plus 1, which is g of 2x plus 1. Put t is 2x plus 1, then x is t minus 1 over 2. This shows that g of x is x minus 1 over 2 if x is odd. Thus, g is t of x, x and x minus 1 over 2. If x is even, if x is odd. Perfect. So it was 1, 1, and then it has the left inverse, and then we have found the left inverse. Perfect. Number 2. 2 says, note that f of x is mod of x plus x greater than 0 for all x and z. This shows that negative integers do not belong to image of f. negative integers do not belong to image of f, which we denote by this. In particular, f of x will never be -1 for all x and z. Thus, f is not onto z, and so f does not have right inverse. Perfect. Exercise number 3. Says that let x and y be non-empty sets and f from x to y is a function if t is subset of x, then f of t denotes the set f of x, given that x is from t. F of t is called the image of t under f. Prove that f is 1, 1 if and only if f of a intersection b is f of a intersection f of b for all non-empty subsets a and b of x. For all non-empty subsets a and p of x. We took two sets. We defined a function f. Then we said we have a subset of x. Then we define a function f on t. We applied a function f on t, and then there's this f of t will have these kind of elements. So this f of t is called the image of t under f. Prove that f is 1, 1 if and only if this property is true for all the non-empty subsets a and b of x. To do that, you need to make sure this is true, and this is if and only if. So we can suppose one part and then prove other part. So let's try that. Solution. Suppose f is 1, 1 and let A comma B are non-empty subsets and A comma B are subsets of X, let Y belongs to this F of A intersection B. Then Y is F of X for some X in A intersection B, right? Because, yes, hence Y also belongs to F of A intersection F of B. Yes, thus F of A intersection B is subset of F of A intersection F of B. The one part is proven. Now, let Y is from A, F of A intersection F of B. Then Y is in both. Thus, Y is F of A for some A in A, and Y is F of B for some B in B. Yeah. Now, since F is 1, 1, and F of A is F of B, we find that A is B. A is B. Thus, if indeed belongs, sorry, Y indeed belongs to F of A intersection B. Hence, the other part is also subset of F of A intersection B. And consequently, they are equal. So we are managed to prove the one part of if and only if statement. Now we will assume this part and then prove that F is 1, 1. So conversely, suppose that F of A intersection B is F of A intersection F of B for all subsets, for all A comma B in X is subsets of X. Now suppose on contrary that F is not 1, 1, then there exists X comma Y in X such that F of X is F of Y and X is not Y. Let A contains X only and B contains Y only. Since their intersection is phi, f of A intersection B is also phi. However, f of A intersection f of B is the set which contains f of X. It's not phi, which is not phi. Thus, f of A intersection B is not equals to f of A intersection f of B, which is a contradiction. Hence, f is indeed onto. Sorry, 1, 1. Number 4. We have a non-empty set. Let A is non-empty and E be an equivalence relation. On A. On A. Let B is a set which contains complete number of set elements, i.e. B contains is the set of all equivalence classes with respect to E. Prove that there exists a function f from A into B into B. The set B is usually denoted by the set B is usually denoted by A quotient E. Solution. So we define if A to B by f of X is an equivalent class for all X in A. By definition of f, the domain of f is A, and let x comma y in A. Suppose both are equal. X is y. Then the equivalence class of x is equivalence class of y. And so f of x is f of y. Thus, f is well defined. Now let the equivalence class of A which belongs to B, then A belongs to A, and f of A is the equivalence class of A, hence f is onto B. Perfect. So indeed there is a function. Thank you so much for joining this lecture. Do watch it and subscribe it. If you subscribe it, it will be easy for me to make more videos. Thank you. Bye.